When I think about stacks, mostly I would think about the stack data structure. But when you solve more and more problems, you would begin to realize that there is actually a coding pattern by which you can identify that, okay, I need to apply stacks over here. And that is what we're going to explore in this video. Hello friends, welcome back to my channel. The first thought that comes to my mind is a stack of plates, because that is really easy to visualize and you can see the last in first out principle being applied. In a cafeteria, all of the plates get collected and then the plate on the top is the first one to get washed. So that is the basic idea how a stack data structure looks like. Basically, you will have some kind of a structure where you store all of your elements and then you are supporting some particular operations. For example, the peek operation. You are just accessing the top element but not removing it. Then you have the pop operation. You pop out the element from the stack and then you want to use it somehow. Next, you have the push operation. As soon as you do a push, this element will go on the top of the stack. And after that, we all know about the LIFO principle, or the last in first out. The last element that gets added at the top of the stack, this is the first element to pop out. This is the basic ideology how a stack data structure looks like. Now, more than just real life, stacks have a very good example in programming as well. The very first example that you might have seen with stacks is valid parentheses. This is a common problem where you are given a mathematical expression and you have to identify if it is even valid or not. Think about it. If I give you a very huge mathematical expression, will you just try to start solving it? What if the expression is not even valid? You want that your process is very fast. You want your program to be efficient. And for a valid expression, the number of opening brackets should be equal to the number of closing parentheses, right? And they should follow a particular order. You cannot have a closing bracket first and then an opening bracket. This is invalid. So in this particular question, you are given a set of parentheses in which they are appearing and you have to tell me if this is valid or not. So how do you usually go about solving this problem? The idea over here is that you take up a stack data structure and as soon as you get any of the opening parentheses, you will add it to your stack. So for the first example, I add an opening parentheses in my stack over here. Now move ahead. I get a closing parentheses. Look for the top element of your stack. If they are matching and they complement each other. For example, this is the opening bracket, this is the closing bracket. Everything is good. So I can simply remove this bracket from my stack. Next, I see an opening curly brace. So I add this to my stack. And then going forward, I have a closing brace. This is the same in the stack, so I can remove it. Next, I have a square bracket. And then when I move ahead, I have a closing bracket. I match it and okay. I'm able to remove this as well. I have iterated all the parentheses and my stack is also empty, so everything is good. This is a very basic example. Let us look at one complicated example and see what is happening. You just have to follow the rules that I just told you. As soon as you see an opening parentheses, just add it to your stack. Again, you have an opening brace, so add it to your stack. Next, you have an opening parentheses again, so add it to your stack. Now see, you are getting a closing bracket. Match it to the top element of your stack. They are complementary, right? This is closing and this is opening. So what you will do is you will just remove this element. Next, you have an opening square bracket. So let us add it to the stack. You just have to follow simple rules. Then you have a closing bracket, you match it, it matches, so I will remove this. Next, I have a closing curly bracket, it matches, so I'm going to remove this as well. The next element is an opening curly bracket, I add it again. I have a closing bracket, so this gets removed. And notice, I have the last element as a closing bracket. I have this in my top of my stack, so I will remove it as well. So what have I done? I have traveled my entire expression and my stack is also empty. That means this expression was valid. Think about it. If there had been any other bracket somewhere in middle, if I had an opening bracket over here, then what would happen? I would still have one opening bracket dangling in my stack over here. That means my expression is invalid. So just by these simple checks, a stack is helping you to identify if your expression is valid or not. And this is one of the most basic use cases that you would have seen with a stack data structure. But definitely, as you solve more and more problems, you will see more applications of the stack. For example, the problem min stack. What is special about a min stack? It will have all of the same operations as a stack data structure. You will just have one additional operation that you have to implement, get minimum. The idea over here is that as soon as you call get minimum, it should return me the minimum element that I have encountered up till now. So how can you make this happen? If you have a normal stack and this is the input sequence that you're getting, what will happen? All the numbers will start coming in 1, 5, minus 3, and then an 8. If someone asks you, okay, what is the minimum element? Then you cannot just iterate over a stack. You will have to pop all the elements, find the minimum, return them, and then pop them back again. This means you are having so many useless operations. How can you optimize it? The idea over here is that you take the help of one more auxiliary stack. And this stack will keep a track of every minimum number that I have found up till now. So let us try to go over this again. I get the first number and this is 1. For now, this is the minimum number, so I will add it to my min stack. Next, I have the number 5. Add it to your regular stack. That is fine. But check the top of your minimum stack. 5 is greater than 1, right? That means my minimum element will still be 1 out of these. So I do not want to update it. I will let 5 live only here. The next element is minus 3. Add it over here. And then, should you add minus 3 over here? Yes, because minus 3 is even less than 1. That means up till this limit, I have a new minimum. So I add minus 3 here. Then next element is 8. So you just add it over here. Next element is minus 1. But I still have a minus 3 which is even lower. So don't add it. Up till now, everything is good. As soon as someone says, okay, get me the minimum. Instead of looking in this stack, look in your min stack. And you can tell them, okay, minus 3 is the smallest number up till now. And that is how you can make use of a helper stack. For example, what happens if I try to pop from my stack now? Let us say I do a pop operation, so minus 1 gets out. But at the same time, you will check your minimum stack also. Are you popping the same number? No. So leave the minimum stack as is. You pop out the next number and that is 8. You don't have 8 in your min stack, so let it be. The next number you pop is minus 3. So you remove this. But in your min stack, you have minus 3 here as well. So you will need to remove minus 3 also. That is how this stack and this stack will maintain kind of the same state. If someone asks you, give me the minimum, you will not return minus 3. You will return 1 because out of the remaining elements of the stack, you have to tell me the minimum. That is why you will look at both of these stacks simultaneously and then perform your operations. If you have more elements coming in, let's say 10 comes in, you add a 10 over here. Then you have minus 99 coming, add a minus 99 here, and then you're gonna update your min stack as well. That is how you keep on doing it, and you can return the minimum element in just order of 1 time. I know it will take up an extra space of order of n, but that is fine. We are compromising on the space for a better time complexity. So what did we do here? We took a helper stack and that helped us to achieve our goal. When you think about stacks, one other data structure immediately comes to your mind, and that is queue. A queue follows a first in first out policy. So you might have seen a problem like this. You have to implement a queue, but you have to use stacks. Naturally, you cannot make that happen just by using a single stack. So let us assume I am taking one more helper stack and I have to somehow perform these operations: nq, dq, and peek. Peek simply means looking at the top element. So now let us say I am adding some elements in my queue. Let us say I add the elements 5, then 8, and then a 16. What will happen in a queue? In a queue, 5 will be the first element to pop out. But in your stack, what will happen? You have 5, and then an 8, and then a 16. If you try to pop, 16 will get out. So these are not the same. This is where your helper stack comes in handy. When you are enqueuing elements, just keep them adding to your primary stack. Don't do anything. Now, when you have to look at the dequeue operation, this is what you need to do. Just follow the rules. For a dequeue operation in a queue, 5 will get out, right? Over here, I have 5 at the very last. As soon as you get a dequeue, take up all of these elements and put them in your helper stack. So what will happen? 16 will get here, 8 will get here, and then 5 will get here. Now what do you do? As soon as someone says you, okay, DQ, you need to return me an element from this particular stack. So 5 will get returned. What did we do? We were able to simulate a queue using just stacks. Now let us say more elements come in. Let us say 23 came in and then 42 came in. Remember what I told you. Whenever you are having NQ operations, just add these elements to your normal stack. Now let us say someone calls DQ. You will return an 8 over here, right? But what do you do this time? This time this helper stack is not empty. So you do not want to transfer all of the elements until your stack is empty. If someone says DQ, look in your helper stack. If there are elements, return this. So what will happen? 8 gets out of your queue and 8 gets out of this particular stack as well. We are having a 1-to-1 operation, correct? If someone says DQ again, 16 will get out of the queue and 16 will get out of here. So we are having a feature parity. Now if someone calls a DQ, this time 23 will get out, but your other stack is now empty. So first of all, you will need to pop all of your elements from the current stack to the helper stack, and then you pop out an element, and then 23 will get out, and you will have maintained the same kind of feature using 2 stacks and a queue that you didn't even have in the first place. The peak operation is also very similar, and I believe you can figure that out on your own. So what are we doing up till now? We are just exploring some of the basic applications of a stack. For example, we are matching parentheses. Once you are done matching parentheses, you can also use it to evaluate expressions. You will just use the same stack to solve small portions, and then you get your result from it. Similarly, you can also think about parsing code. A code also has brackets, right? And this is the same as matching your parentheses. That is how a compiler knows that, okay, one of the bracket was not matched. And similarly, you can think about tracking histories as well. For example, you have your undo and redo buttons. What do they do? The undo button keeps a stack of each of the operation that you have done. And when you do an undo, it will look at the topmost operation and then it will keep on going down till you keep clicking back. Once you are clear with all of this, it is actually time that you dive into some of the advanced concepts which are solved using a stack data structure. For example, you might have heard of the problem next greater element. Basically, you are given this particular array and you have to tell me the next greater element for each of these elements in the array. What does that mean? For example, when I look at 3, I will start to traverse, and what is the next greater element I can find? It is 5. So for my answer, I will write down a 5 over here. For 1, what is the next greater element? It is 5 again. So I will write down a 5 here. For 5, what is the next greater element? I keep going, I find a 7. So I write down 7 here. For 2, what is the next greater element? It is 7 again. So 7. For 1, I have 7. For 0, I have 7. For 7, I have 9. For 9, I do not have any greater element. That means I can write down a -1 over here. It just depends upon the problem you are solving. For 2, I have the next greater element as 3. And for 3, I don't have anything, so I can write down a -1 over here. This is the answer that I'm expecting. But how do you reach here? If you have already noticed, for finding the next greater element, we are always going from the left towards the right. And it is certainly possible that you might have to go all the way to the end for every element to find out the next greater element. So think about it. What if we start from the very back and then try to build upon our solution? That can maybe give us a small hint and maybe help to solve efficiently as well. But how do you get an intuition that I might need a stack data structure over here? Remember that I told you we have to go from the reverse direction. And if I will take up a stack and add all of the elements in a reverse direction over here, what will happen? The topmost element will be somewhere over here, right? It will be the leftmost element. And think about it. That is what I need to explore also. For example, when I look at 3, I may not want to go all the way to the end to find a 9. I could have found a next greater element somewhere earlier. So these elements should be somewhere on the top of the stack. And all of these elements should be somewhere at the lowermost portion of the stack. We are still gonna decide how to add and remove elements from the stack, but this is the general idea. So how do you start? Let us try to build our output array again. What is the first element I see? I see a 3. My stack is currently empty. That means I do not have any greater element. So what I can do is I can write down a -1 over here. And I will add this element to my stack. So 3 gets added to the stack. Now go ahead. Look at the next element. Next element is 2. Check your stack. Do you find a next greater element over here? Yes. So what I can do is I can write down 3 over here. This is the next greater element, correct? But also, this 2 itself, it might be a next greater element for some of the previous elements. I don't know yet because I haven't seen them yet. So I will want to keep it in my stack also. So I will write down 2 in my stack over here, correct? Look at the next element. The next element is 9. Check the top of your stack. Do you find any greater element? The top element is 2. It is not greater. So what I can do is I can remove this element. Why? Because I know that in my stack, I will have stored all of the greater elements at the very end. So I need to keep popping the elements until I find a greater element. And this is why this stack is called a monotonic stack. At every instance, I will ensure that this stack has increasing number of elements when I keep popping them. If I pop the next element, that is 3. 3 is also less than 9. So I will remove this element also. Now my stack is empty. So I can say that I don't have any greater element than this. And I will add this 9 to my stack. Just wait a little while and everything will become clear. What is the next element? That is 7. So check. Can you find a next greater element in your stack? Yes, 9 is greater. So I can write down 9 over here. Also, what I will do is I will add this 7 to my stack because this 7 could be a next greater element to some other element that I yet have to see. Look at the next element. It is a 0. Check in your stack. Do you find a next greater element? Yes, I didn't have to pop. So I can straight away use this 7. So I write down this 7 here. Also, I will add this 0 to my stack. Notice what is happening. This stack is always monotonic. It will have elements in an increasing order every time. And I'm doing this so I can reach at my solution. Look at the next element. It is 1. Check your stack. Do you find a greater element than 1? No. So what did we do? Our stack has all the elements in an increasing order. So I know that if I pop elements, I may find the next greater element over here. So I will remove this 0. Do I find the next greater element? Yes. So I will write down a 7 over here. And what I'm going to do is I will add this 1 over here. And once again, we do this because it might be possible that this 1 itself is a next greater element to some other element that we haven't yet seen. And your stack is still in an increasing order. Notice the next element, that is 2. Do you find a next greater element over here? No. So I can remove this. Do you find a next greater element here? Yes, that is 7. So I can write down a 7 over here. And I will also write down a 2 in my stack. Check out 5. Is 2 the next greater element? No. So I will remove this. Is 7 the next greater element? Yes. So what I will do is I will write down 7 again. And this 5 gets added to the stack. Notice how our stack is always monotonic. It is always increasing in nature. Now I have 1. Check the next greater element. Yes, you can find it, 5. So no need to worry. I can simply write down over here. And at the same time, add this 1 also to my stack. For the next element, you see 3. Is 1 the next greater element? No, because 1 is smaller. So I remove this. Check the next element. Is 5 greater? Yes. So I will write down over here. And that's it. I have traversed my entire array and I use this monotonic stack to get my same answer. If you notice, they both are the same. So what are we doing over here? We took an advantage of the fact that this stack can hold all the elements in an increasing order. And the pop operation is ensuring me that I get all of these elements one by one. Make sure to pause this video right over here and understand this concept of next greater element. This is a very good use case, and you will find a lot of problems that utilize the same concept in one way or the other. And that is what makes monotonic stacks very, very important to understand. For example, you might have seen one more problem on LeetCode, and that is called daily temperatures. I will now show you how this problem is very, very similar to finding the next greater element. Basically, what happens is you are given a temperatures array. All of these are representing the temperature on a certain day. The temperature on first day is 73, then 74, 75, and so on. You have to tell me after how many days will I get a warmer temperature. So if I try to just brute force this problem, for the first element, after how many days do I get a hotter temperature? After just one day. So I will write down a 1 over here. For the next element, after how many days do I get a hotter temperature? 1 day. So I will write down 1 here. For 75, after how many days do I get a hotter temperature? So 1, 2, 3, and then 4. Because 76 is greater than 75. So I write down 4 here. For 71, 1, 2. For 69, just 1. For 72, just 1 again. For 76, I do not get a hotter temperature. So for this particular problem statement, you have to write down a 0 here. And then for 73, I again do not get a hotter temperature. So once again, I have to write down a 0. So while going through this, what did you observe? Tell me. Is this problem anywhere related to temperatures or getting hotter? No. All you are doing is you are finding the next greater element. For example, for 73, you are finding the next greater element to be 74, then once again 75, then once again 76. You are finding the next greater element, right? But instead of writing the actual values, you don't have to write 74, 75, and 76 here. All you have to do is you have to tell me after how many days do I get that temperature. So what are you doing? You just need to find out the index difference between these two things. So instead of storing the actual numbers in your stack, what you can do is you can also store the positions of each of the number. By that, when you are iterating backwards, as soon as you find 75 and you find 76, for this particular problem, 76 will have a position associated 6 and 75 will have a position associated 2. So 6 minus 2 gives you a 4. And that is it. This problem is literally the same. If you understand monotonic stacks, you can solve this problem really easily. And monotonic stacks usually work around the same principle. Basically, first of all, you initialize the stack, then you will try to scan through all of your elements. And then the most important condition is you have to maintain your monotonicity. You have to find out how to pop and how to push elements such that the stack maintains its state. You resolve and you find the next greater elements or the next smaller elements based upon your condition. And then you want to update your stack. This is how we are maintaining the state. And this loop just goes on. This is the idea how monotonic stacks actually work. And this particular concept is very, very essential. I keep repeating the fact because I have seen a lot of very hard problems. But once you have figured out, hey, this is the solution, they become really, really simple to solve. And I want to take up an example problem which I have found very hard myself. Just reading through it, I wasn't sure what is happening. And I will try to break it down as much as possible. But remember, the underlying idea of a monotonic stack will still remain the same. Let us see if you are able to figure it out. The problem I'm talking about is called trapping rainwater. Over here, you are given a certain array. And this array is representing the height of each building. So building 1 has a height of 0, building 2 has a height of 1, then 0 again, then 2, then 1, and so on. So basically, if you will try to map all of these heights on a grid, you are trying to see a horizontal section of a city. So the first building doesn't have any height. The next building has a height of 1, then again 0, then a height of 2, then a height of 1, then 0, then 1 again, and this time you have a height of 3, then 2, then 1, then 2, and then 1 again. So you are kind of looking at the horizon view of a city, right? You might have seen this kind of a view. Our city kind of looks like this. And now what happens? This is where the programming part begins. You have to treat all of these cities or towers as containers or walls. And water just came down. So basically, it started to rain. And when it rains, what will happen? Water will get filled up in all of these places, right? Notice what will happen at the very end. Since you do not have any wall here, all of this water will just flow down, correct? And similarly, check out this height. You do not have any building or any wall here. So the water will simply flow out. You have to remember these things. What about this particular section? You will fill water over here because it is bounded by two places. But you cannot get any top because any water that comes here, it will just start to flow down. For this particular section, you will have a lot of water here, and then any additional water will start to flow down and it will ultimately flow down over here. So after it has rained, how much water is trapped? You are looking at this particular cross-sectional view. This is the ultimate amount of water that will get trapped, correct? Notice, I cannot have any water over here. Any water I have here, it will start to flow down because there is no wall. So it will flow down from here and then from here. Similarly, I could not trap any water here or here. It simply flows down. And same is the condition for this section as well. The only water I have trapped are these units. And you have to tell me, given this array, how much water have I trapped? In this particular problem, how much water did I trap? I trapped a total of 6 units. 1, 2, 3, 4, 5, and then 6. So for this particular test case, 6 is your answer. Now the tricky part. Where do you even begin solving this problem? There are so many different ways to approach it. How do you start to even calculate the water at a particular place? To understand it, let us focus on the very basic concept. For example, when I'm looking at just this particular section, how much water is it gonna trap? You have a wall on the left and you have a wall on the right. You know that you will only trap the minimum height because any height greater than this, the water will just flow. This is giving you the height that you can trap. And how much water can you trap above the ground level? If you are at ground zero, then simply high minus low, and this is the water you are trapping. But check out this particular unit. You see that you have a wall of height 2 on the left and you have a wall of height 2 on the right. But can you trap 2 units over here? No, because this building already has a height of 1. So how much water you can trap? Whatever is the minimum height out of left and right minus your current height. Once again, check out this particular location. Your left has a height of 2 and your maximum height on the right is 3. But can you trap all of this? No. You have a left height of 2 and right height of 3. You will only be able to trap the minimum of these. So you can trap a maximum of 2 units. But you're already elevated 1 unit. So for this particular block, you can only trap 1 unit. And that is the building block of this particular question. Instead of looking at areas, you need to look at each of these individual units and try to determine how much water can I trap in each of these individual units. It could be 0, it could be anything. And then you just add all of them. So this is what we have right now. We are finding out the water at ith location. And ith location is each element in my array. And how do you find it? You find the minimum of maximum of left and maximum of right. What does this mean? For example, when I am standing at this particular location, what is the maximum height I can find on left? This is my maximum height. And what is the maximum height I can find on right? This is my maximum height. So maximum left is 1 and maximum right is 2. I want the minimum of these. This. So I get this and minus the current height. The height is 0. So I trap 1 unit of water here. Notice what happens for this particular condition. I am finding out the water at I. So what is the maximum of left? On the left, I don't have any value that is higher than 2. So this becomes 0. And on the right, do I have a maximum value? So on the right, I have a value of 3. So max right is 3, but minimum of these is 0. So if this is 0, I cannot trap any water. And that's it. That is what I'm seeing. I'm not able to trap any water here. That is how you have to go on for each and every location. But where are stacks coming into the picture? If you have already noticed, and if you're observant enough, how do you find out the max left and max right? What are actually max left and max right? These are the next greater elements towards the left and next greater elements towards the right. So when you're looking from over here, what will you find out? For each location, you are finding out the max right. I have evaluated the max right for each of the indexes, and this happened in order of n time. How about finding out the max left? This time you have to solve the same problem, but you're looking at this particular direction. And this is simply, you want to iterate from this direction and keep a monotonic stack. So you are just solving the same problem twice. You're looking from the left and now you're looking from the right. So what do you have now? You have the max left for each of these indices and you have the max right for each of these indices. Now what is left? You just have to apply this formula at each of these indexes and find out the total water. Notice that if any of the value is 0, you can simply discard it, because if you are not having any wall, then you cannot trap any water. So some of the indexes will just simply rule out, because in all of these, one of the element is 0. And how many are we remaining with? Notice that wherever we have water, we have some value for left and right. To find the total water, calculate all of these values. Now you have everything, and I will leave the last part to you as an exercise. You notice how we can use the stack data structure in so many different places, especially a monotonic stack. This way you are ensuring your stack has always greater elements or smaller elements. And the concept of a next greater element can be used at a lot of different places. Just tell me in the comment section below, where all have you found this particular type of concept being used? This will become a very good collection, and I would also love to discuss all of this. As a reminder, if you found this video helpful, please do consider subscribing to my channel and share this video with your friends. This really keeps me motivated and I can make more such videos. Also, a huge shout out to all of the members who support my channel. You guys really keep me going. And as a member, you do get priority reply to your comments and early access to new videos as well. Also remember, you can now schedule a one-to-one session with me and we can chat about anything. Stay tuned for my upcoming video. Until then, see ya.